A projectile is defined as anything that freely moves through the air, ignoring air resistance. And so what we're really talking about is anything that freely moves through space affected solely by gravitational effects. So in other words, nothing with a motor or a propeller giving internal energy in order to affect the airborne motion. What we've seen in a previous video on vector resolution is that perpendicular vectors can represent the overall vector of motion, and what we know from previous analysis in Newton's laws is that perpendicular vectors are independent of one another. And so suppose we have a ball at the top of a ledge and someone kicks it from the top and it arcs into the air and falls down. What we track as motion is the trajectory of this ball like this. But if we think about it in terms of velocity, the initial velocity, v naught, would look something like that, going up and to the right. But as the ball moves through space, we actually see this vector change from v naught to various other component values. And so what happens, though, is there's an odd phenomenon where part of the vector remains the same and part of it does not. And so if we trace a few more spots on here, we see a couple pieces of the information happening. So if we trace the fact that v can actually be represented as two motions, we see that here it's going to the right, 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 and here it's going to the right. And what you'll notice is if I drew this more carefully, this to the right vector would be the same length the entire time. And so the horizontal velocity, Vx, actually remains constant. And you can imagine that the similarities between kicking a ball off a rock like this and rolling a ball on a flat level surface at some horizontal velocity, the ball would continue at that continuous speed. So horizontal velocity, Vx, is constant. And that's something we've already studied a good bit. The only distinction now is that we're adding in horizontal motion while also noticing vertical motion. And so when we analyze the vertical motion, we see that here at the beginning, it has some initial Vy naught. But here, the Vy has reduced. Vy has reduced. Here, Vy is 0. Here, it has inverted. Now the velocity is going down in the Vy direction and still horizontal in the Vx direction. Here, the velocity has increased even further to the Vy direction, while the Vx direction has remained constant. So what we see is that the vertical velocity slows down until it peaks at the apex or the highest point, and then the vertical velocity speeds up in a negative way coming back down. And if you haven't realized already, that's due to the fact that a in the y direction is equal to g, in this particular case, as negative 9.8 meters per second squared. That's based on a frame of reference now where we're looking at two dimensions, calling this the positive x and calling this the positive y, as we saw in our vector resolution analysis. And so now what we're going to be doing is separating the vertical velocity from the horizontal velocity in order to conjunctively analyze motion that is both horizontal and vertical, right? And so what we really need to be able to do is just separate those variables and keep things organized. First key is recognizing that in the y direction, the acceleration is negative 9.8 meters per second squared, so pointed this direction. And if we added in an a vector onto each one of these, the a vector would be constant no matter the location of the ball the entire time. Since Vx is demonstrated to be constant, we also recognize that the acceleration in the x direction is equal to 0. And that's very useful because that narrows down our choices of formulas to describe the motion as a simple v equals d over t relationship. Now, in this case, we're calling this tx, and if we analyzed our vertical motion is governed by a equals g. So in the y direction, we have all of our free fall problems based on an acceleration that's known. So we know that Vy is equal to Vy naught plus g times t, just substituting in g for a. And then, of course, we have Vy squared equal to Vy naught squared plus 2 times g times dy, where dy would be represented by the vertical height at each position along Vy, right? And so dy initial here is the ball's displacement as it moves from there to there. This would be dy, or its height here, etc., right, depending on where we're describing our speeds. And then, of course, we have our dy equal to Vy naught t plus 1/2 gt squared. Now, the only thing that really is standing out here is the fact that when we analyze these as separate analysis, it really seems that there's two sets of equations and two sets of analysis. And that is true because of the fact that the acceleration is separate in the two directions. And so what we'll need to do first is vector resolution in order to isolate our vertical and horizontal components of our speed. Then we will not use this green V naught again, right? You will only use Vx and Vy naught because perpendicular vectors are independent. So the Vx under constant speed is moving with this formula, whereas Vy is moving with these formulas that we see here. So when you go through and make your list, now you're not going to just make a single list. It's important to make a list that represents both your x and your y direction. So in the x direction we have Vx, we have dx, and we have tx. And in the y direction we have Vy naught, since it accelerates, to Vy. Then we also have ay, which we know is g, and of course dy and ty. Now the key here is recognizing that the time it takes for the ball to move from here simply horizontally across to here at its final position, tx, is the same amount of time it takes for the ball to move up and then fall back down to this position here. The reason being, of course, there's only one ball. And since there's only one ball, tx and ty are the same value. And so when you think about it as a system of equations, we can drop the x here and the y here and here in order to relate these equations to that equation. And so it's very useful to recognize that tx and ty can both be identified as just simply t, and this are how we link the two sides together. So if you're given enough information to find information about the horizontal motion, you can fill in this side of the table and then transmute t to this side of the equation and then repeat the process in the vertical analysis. And we'll see some examples in class in order to put this all to the test. The key component here is going to be organizing your information as it is seen on the diagram into both horizontal and vertical components of both V, D, A, and T. Be careful to utilize your vector resolution at the beginning in order to find Vx and Vy naught based on your original V naught, and then be careful to let that go so that you are not tempted to use that speed anywhere down here. That's why using the subscripts is so useful. Stick to the subscript notation, organize your table, and you'll find that the problems of projectiles in 2 dimensions is just simply a combination of 1 dimension and vertical freefall.